We are going to be looking at examples 1 and 2 in your section 3.5 notes. Our first step is going to be to isolate the trig function, and then we're going to solve for the variable. So in example 1, this one is really nice. The trig function of tangent x is already isolated. So we need to try to find the x value that will make the tangent equal to the square root of 3. So first thing to note is that this is a positive, and that tangent is positive in quadrants 1 and 3. So those are the two x values that we're looking for initially. Okay, so if I go ahead and draw my triangle in quadrant 1 for this, remember the tangent, you may want to put a denominator of 1 just to help you out there, is opposite over adjacent. This is one of our special triangles that gives us the hypotenuse of 2. Okay, we also have x value down in quadrant 3. Okay, so same thing, tangent is opposite over adjacent, but this time we need both of those to be negative to end up with a positive answer, and because we're going down, and then on the negative x-axis, the hypotenuse will still be 2. Okay, so the good news is we know what our reference angle is. So we have across from x here that our reference angle is going to be 60 degrees, or rather pi over 3, since we want our answer in radians. Okay, so if we were in quadrant 1 and they said just to find a quadrant 1 solution, we could put pi over 3. Okay, if we had to be in quadrant 3, we would need to add pi to pi over 3, and we'd be down at 4 pi over 3. Now, our instructions say to find all solutions. So we have to remember for tangent that every 180 degrees that the solution repeats, because of the period being pi. Okay, so initially you might think about the first quadrant and saying, okay, we got pi over 3, and if I make a complete circle back to pi over 3, okay, and that's 2 pi, making a complete circle. And then you can just keep making circles, 1 circle, 2 circles, 3 circles, etc. Usually we use n to talk about that, where n is any integer, and our notation for integer is this, okay, symbol. All right, so in quadrant 3, we can think of the same thing, that x is going to be 4 pi over 3, and then every time we make a circle, we get back to that same spot. Okay, but like we said earlier, the tangent repeats its cycle every 180 degrees or every pi. So the best way to write this is not to think about a complete revolution, but to think about a half revolution. Okay, so when we put this together, we can say, all right, we start in quadrant 1 at pi over 3. The 4 pi over 3 will come up in half of a revolution. So instead of putting 2 pi in, we can put pi in for every integer. Okay, and that kind of puts together those two answers. All right. Okay, now moving on to example 2 here. Okay, in example 2, our variable with the trig function is not isolated, but it's easy to do. We can subtract the 3 sine x over to this side. Okay, and we get 2 sine x minus 1 equal to 0. Then we can go ahead and kick that over, and we get 2 sine x equal to 1, and then divide by 2 and get sine x is 1/2. Okay, so now we got to go through a similar process. Since our answer is positive, we want to think about where the sign is positive. Definitely in quadrant 1, and then we also have quadrant 2 where the sign is positive. If you need some help with that, remember all students take calculus, an acronym that we learned. So this is why I know the sign is positive there. Okay, this is how I knew the tangent was positive in quadrant 3 in example 1. And this is for the cosine down in quadrant 4. All right, so I'm going to go ahead and draw my pictures. I have an x in quadrant 1 and an x in quadrant 2. I know that the sine is opposite over hypotenuse. Okay, this is also going to be another special triangle. I can fill in that side as root 3. Okay. okay? Similar triangle over here, except we'll have a negative root 3, okay? All right, so I want to ask myself what my reference angle x is in this case. So since x is across from 1, I'm going to think of 30 degrees, or in radians, I'm going to think pi over 6. All right, so if I'm trying to give a quadrant 1 answer, like we talked about in example 1, every time we make a complete revolution, we get back to the same angle. So since sine's period is 2 pi, we're going to have to write pi over 6, okay, plus 2 pi n. And we can make as many circles as we want, okay? So remember, this notation is for all the different integers, okay? And then for our quadrant 2 angle, so if we have pi as being our straight line mark, if we take off the pi over 6, we'll get an angle of 5 pi over 6 in quadrant 2. And then we need to think about every time we make a revolution, we get right back there. So we'll have the plus 2 pi n, where n is an integer, okay? And that does it for example 2.